Hello everybody, and welcome back to another Algebra 2 Big Ideas lesson. This is actually the last one of Unit 4. We made it so far, so give yourself a pat on the back. These notes are going to be a little bit shorter, but there's two things that we are going to be talking about. They're both going to relate to how we can use polynomial models for real-life data. Math is nice. It's good for math things, but we want to relate this to real life. And it turns out there are a ton of things that polynomials can be used to model in real life. Today we're going to be focusing specifically on how it relates to finances, like the stock market and things like that, but there are a million different things that polynomials can be used for in real life. We're going to see how we can turn data into polynomials. First things first. On a separate sheet of paper, I want you to copy down these three tables and give yourself some space to work in between them. Hopefully you've had a chance to copy these down. If not, pause the video. I want us to try to figure out what types of polynomials these are. But Mr. Strager, how can we determine what a polynomial is just from a table? Well, remember that polynomials take certain shapes. For instance, if I gave you a polynomial like this, it's a quadratic. Polynomial like this, it's linear. Polynomial like this, it's cubic. Polynomial that's a weird parabola, funky parabola, it's a quartic. Each one of these have different rates of change. Like this one goes down and back up again, but it's in a pattern that makes it symmetrical. These ones are also patterns of going up and down. So if we can figure out how much we're increasing or decreasing by, we might be able to figure out what type of polynomial something is. Let's get to it. First things first, on all of these, the x values all change by the same amount. They're going up by ones. This is very important. We want to make sure that we're going up by the same amount each time on our x's so we can accurately see how things are changing. If we're not going up by ones, you might need to do some filling in the table. Like for instance, if I told you that 10, for example, was negative 17, you would have to fill in 9 using the patterns you know. Let's take a look at these patterns, though. I start at negative 3, and I go to negative 5. So how much is that changing by? Well, this goes down 2, negative 2. And I go from negative 5 to negative 7, it's negative 2. And negative 2 here, and negative 2 here, and minus another 2 here. We start to see a pattern emerge. This is called the first difference. The first difference is just the change in your y's. You might have also heard it called the rate of change or the slope. If your first differences are all the same, you have a degree 1 polynomial. And what do we call a degree 1 polynomial? Something that just has an x in it. No x squareds, no x cubes. We call it linear. If your first differences are the same, you have a linear function. Isn't that neat? Let's see if that transfers over to the next one. So in the next one, we look at the differences. To go from 4 to 1, we minus 3. To go from 1 to 0, we minus 1, and uh-oh. These first differences are not the same. Negative 3 and negative 1 are not the same. So we immediately know this is not going to be linear. Let's fill in the rest, because this is going to help us figure out what it actually is. Over here we get plus 5. Super weird. The first differences didn't do anything. But we can find the second differences, the differences between these differences, and see if that is constant. To go from negative 3 to negative 1, I add 2. To go from negative 1 to 1, I add 2. 1 to 3 is adding 2. 3 to 5 is adding 2. It's all 2's. This is called the second difference. And if your second differences are the same, it's a degree 2 polynomial. And what do we call a degree 2 polynomial, where the highest exponent is squared? We call it a quadratic. So if your second differences are the same, it's a quadratic. We've learned this before. But did you know the pattern continues up forever? Try this example here. I want you to start off by pausing the video and trying to find the first and second differences. Go for it. Hopefully you've had a chance to try these out. This one is super weird. So we go from plus 14 to plus 2 to plus 2. Oh, we got some kind of pattern. To plus 14. Okay. To plus... that's plus 38. These first differences are not the same, so it's not linear. Let's try the second differences. The second differences are as follows. If I take the difference of these differences from 14 to 2, that's minus 12. From 2 to 2, that's just plus 0. From 2 to 14, that's going to be plus 12. From 14 to 38, that's plus 24. It's not quadratic either. But some of you may have been able to notice there is still a pattern here. In fact, if we take the third differences of this one, from negative 12 to 0, that's plus 12. From 0 to 12, that's plus 12. From 12 to 24, that's plus 12. The third differences are the same. So what does this mean? If the third differences are the same, it means you're looking at a degree 3 polynomial, which we call a cubic. The pattern continues up forever. It's really interesting how it works. And to those of you who really want a challenge, you can feel free to try out this problem. This is a crazy one. But try to figure out what degree this is. Try to figure out which differences are the same. Believe me, it works. I've just tried it. But it's a little bit of a tougher one for those who are looking for a challenge. To those who aren't particularly looking for a challenge, let's take a look and see if we can find something a little smaller. Let's see if we can use our differences to find what degree this polynomial is. Pause the video. Find the first differences, the second differences, the third differences, the fourth, whatever we need until we get the same number. Write down what type of polynomial it is. Pause the video and try it out for yourself. Hopefully we had a chance to try it out. If you have, you would have seen the following. The first differences are not the same. Plus 3, plus 6, plus 10, plus 15, plus 21, plus 28. Not at all the same. The second differences aren't even the same. I mean, if we take a look at this, we're going up by different numbers each time. Here it's plus 3, here it's plus 4, here it's plus 5, plus 6, plus 7. But around here we should start to see a pattern. Around here we should start to see what degree this is going to be. Because if we take all of these differences, they follow such a consistent pattern that it's easy to see. Since it's just plus 1, plus 1, plus 1, plus 1, this is a third degree polynomial, or a cubic. Cool, Mr. Strager, how does it help us figure out what polynomial it is? That's a good point. It doesn't really, does it? So let's do something that'll help us actually make that. Let's do something that will actually help us get there. Everybody, we are going to visit our old friend, the regressions. Quadratic regressions, linear regressions, and beyond. So here's what I'd like you to do. I'd like you to take out your calculator. And as a reminder, since it's been a while, here's how you get to the regressions table. You click on Stat, you click on Edit, And there's a table where you can plug numbers into. So I'd like you to plug all these numbers into this table. Pause the video if you'd like, and take some time to plug in all of these different numbers. Hopefully you've gotten a chance to plug them all in. Since we know it's a cubic function, a linear regression isn't going to do, a quadratic regression isn't going to do, we need something more powerful. If we click on the Stat button again and go to Calc, we'll see that we don't just end at linear regressions and quadratic regressions. We've got cubic regressions, we've got quadratic regressions, we even have some even crazier types of regressions down below. We've got regressions for days. And since it's a cubic, let's take a cubic regression. Bam. We want to use L1 as x, we want to use L2 as y. Here, if we wanted to graph this, which could be cool, this problem isn't asking for it, but I want to show you how to do it. You can always click on vars, go to the right to yvars, click enter, and click enter again, and this will graph it to y1. If we calculate, this is what we end up with for our cubic regression. Little bit weird. Couple things to notice here. We don't just have an A value, a B value, a C value. We have an A, B, C, and D. And the form of the cubic they give us is that it's ax cubed plus bx squared plus cx plus d. We want to write our polynomial in this form, just replacing A, B, and C with numbers. Let me tell you how you could write it, and then I'll show you the even better way of writing it. We could write it as f of x equals, the first decimal is 0.16, so it's 0.1667. I'll use 4 decimal places, why not? Actually, let me write this down where there's a little more space. So we could write this as f of x equals 0.1667 x cubed, because that's ax cubed. Our b is 0.5, so we could write it as plus 0.5x squared. Our c value is 0.33, so we could write it as 0.3333x. And our d is 0, so we don't need to put a plus anything at the end. It's just 0. Those keen-eyed mathematicians may notice that these are actually perfect fractions, just in decimal form. How do we know? Well, for starters, 0.16667 x cubed is 1/6 x cubed. It takes 6 of these to make 1. 0.5 we should all know. 0.5 is just 1/2, so it's 1/2 x squared. And 0.333 we should all know. 0.333333 is 1/3 x. So this is your final equation. Since we stored it, we can see the graph of it. Here's my graph of it. And honestly, I just want to check to see if our fractions work out. If I plug in 1/6 x cubed plus 1/2 x plus 1/3, 1/2 x squared plus 1/3 x. Here you go, so we can all see it. Whoops. Let me move it over so we can see it on the camera. It's going to be like so. And I graph it right alongside our original. We see that the line traces over itself. It's the same graph. Very nice. Usually we don't get numbers this nice. In fact, let's take a look at example 2 and see an exact case where those numbers are not nice at all. Here we have the following. We have a table of the opening values of a stock index on the first day of trading over many years. Let me contextualize this. Let's pretend that this is the company Apple. These are the price of a share of a stock. So for instance, in 1994, it cost $3,754 to buy a share of Apple. In 1995, that was $38.35. In 1996, it was $51.17, and so on and so forth. We want to use a model to estimate this as well. But we can already start to see a little bit of a problem. These numbers are huge. our graphing calculator is going to burst into flames. And in fact, when I tried this on my first attempt at recording, the numbers were so big that my calculator took 5 minutes to load on camera. Not good. So let's think of a different way of writing this out. Instead of using the years 1994, 1995, 1996, so on and so forth, let's use more reasonable x values. Let's substitute all these years for different x values. So maybe 1994 is x equals 1. And 1995 is x equals 2, because that's the year right after. The year after is 1996, so that'll be x equals 3. But we have a gap here. Like I mentioned, it's very hard to find what things are if there's a gap. Let's figure out what x value this gap would cut across to. So if 1996 is number 3, 97 would be x equals 4, x equals 5 would be 98, x equals 6 would be 99, so x equals 7 is 2000. Similarly, we can go and add 3 years to get to 2003, that's x equals 10, and x equals 11 will be 2004. This is so much nicer to put into our calculators. Trust me, our calculator will not, in fact, burst into flames on this one. So here's what we'd like to do. We'd like to put in the numbers 1, 2, 3, 7, 10, and 11 for our x values, and we want to start plugging in our y values. Unfortunately, there's no easy shortcut with this like we did before. So we get the following. If we start plugging all of these in, 5117, we plug in 11497, we plug in 8342, and we plug in 10,454. We can do a regression, but what kind of regression? Thankfully, it tells us. We don't need to find the differences. It tells us to use a cubic model. The thing is, these numbers are not exact. These are estimated values. We're estimating here. So if you tried finding the first differences, second differences, and third differences, even the third differences would not be the exact same. They'd be close, but they'd be off by certain decimals. Or like slight numbers, I should say. Instead, we can use just a cubic regression because it tells us to use a cubic regression. We go cube reg. I'm going to store this as a variable. I'm going to store it as y1, though you don't need to do this. And I'm going to click calculate. And we end up with some insane numbers. Yeah, look at this. We end up getting the following. We end up getting that our a value is negative 16.545. X cubed. Our b value is 173.434. X squared. Our c value is 723.340 x. And we have a d value, a constant, of 2,331.031. This is your cubic model. What a mess. What an absolute mess. And what's messier is, we want to use this to estimate the first day of trading in 1999. First off, what value of x would 1999 be? Well, like 1996 is x equals 3. 97 would be 4. 98 would be 5. 1999 is when x equals 6. So what we're really trying to do is to find the value of the first day of trading in 1999. We are plugging in 6 for every value of x here and calculating it. What an insane ask. This is a lot of calculation to do. Heck, it's even taken me a while just to write down what we're doing. But I want to show you a little bit of a shortcut you can use to calculate anything, to plug in any value of x into anything. Let me show you on your calculators. First off, it is going to require a little bit of typing. We want to basically just replace all of these with 6 and calculate it out very quickly. So here's what we're going to do. We're going to learn a new button on our calculator. If we want 6 to be our x value, here's what you can do. You can type in the number 6, and then down above the on button, there's something that says STO. That is the button for store. This is going to change whatever we decide to store it as into x. So I could turn it into B or G or O. I want to turn it into x because that's what we're actually dealing with. By clicking enter, we now see that x is 6. So even if I type in something like 3x, 3 times x, it gives us 18. This is going to be really helpful because now we can just type in our equation. 16.545 x cubed plus 173.434 x squared plus 723.340 x plus 2331.031. And by clicking enter, we get a number. When we try to find what f of 6 is, meaning we plug in 6 for x, we find that f of 6 equals $9,340.97 thousandths of a dollar, which we can just write as 98 cents. Done. The store button is very, very useful. Pretty cool, right? I'm going to show you an even quicker way, because typing that out was a lot. If you have your equation stored, like we did up here, we even have the exact number stored, we can get an even more accurate answer. All we want to do, whoops, I think my calculator froze up a little bit. There we go. What we want to do is we want to go to vars, go to yvars, click on function, and click on y1. Since x is 6 here, can't we just click equals? If we click the enter button on y1, we get an approximation for the answer. Isn't that cool? This is more accurately what the answer would be if we had typed out the entirety of every single decimal. It makes a big difference, doesn't it? Your answer would be as follows. Your answer would just be 10,363.18. This is why rounding can be a little dangerous, especially with such big numbers. In short, anytime you want to evaluate a function that you have stored in a calculator, you can store it using the store button and recall it using your vars. With that said, everybody, that is the end of Unit 4. If you would like some extra practice, there is plenty in the back of your notes packet. However, that is it. Have a fantastic rest of your day, and I will catch you next time in Unit 5.